Hello and welcome to Heat Pumps, a hot topic for decarbonising Australian buildings and businesses. I'm Rachel Wilkinson, a Senior Advisor with the Energy Efficiency Council. And first and foremost, on behalf of myself and all at the Energy Efficiency Council, as well as our speakers today, I want to acknowledge the traditional owners of the lands across the country that we're meeting on today and pay respects to elders past and present. I'd also like to offer a warm welcome to our international registrants and guests on the line today. And I'd also like to note that this webinar is a part of a collaborative effort between the Energy Efficiency Council and the Australian Commonwealth Department of Climate Change, Energy, Environment and Water, aimed at strengthening Australia's involvement in the IEA's Energy in Buildings and Communities Research Program, or what we call IEA EBC, because we love acronyms in this line of work. So today we're going to be receiving presentations from 3 speakers who are going to be sharing insights for industry and policymakers based on their current research and work. The audience can submit questions in the Q&A function, and we will have an opportunity to answer some of these at the end. Noting that we have a lot of registrations and high attendance today, please be sure to make your questions clear and hit upvote on any questions you'd like to see answered by the speakers so we know what the audience is most keen to hear about. So with that, we will kick off with Candice Hinksman, who is Manager of Demand and Energy Management at Energy Queensland. Candice, if you'd like to take us away. Oh, yeah, I'm not hearing you.
No problem. Thank you for that. I'm just going to share my screen really quickly and kick off. Thanks for welcoming me to the webinar. I'm Candice Hinksman. I am the manager of the demand and energy management teams for the 2 distribution network businesses in Queensland, which is Energex and Ergon Energy. Like other distribution network businesses around the world, we are a network in the middle of a significant transformation. And that transformation has really been brought about by a rapid increase in consumer energy resources. And in particular, we're seeing significant impacts on our network as a result of the rapid and significant adoption of solar PV. Queensland is fairly advanced in the adoption of solar PV, and almost 40% of our customers have PV on their roof, and that puts our penetration in one of the top 2 in the world. You can see a little bit about our current network here, and I'll dive a little bit more into why distribution network businesses care about heat pumps. So this is where we are now in 2024, or now in early 2025. We're coming from an environment where we've got about 5,000 megawatts of solar PV connected into our network. At the same time, we've very recently registered the 50,000th electric vehicle on our network in late 2024. And by 2030, we're looking at the upper end for that forecast to exceed 900,000 electric vehicles on the grid, just almost a million. So the rapid adoption of these consumer energy resources is really having a significant impact on our network peak demand and also on our network minimum demand. And you can see substantial amounts of growth and decay, respectively, for both our peak and our minimum demand. If I go and have a look at a particular zone substation, 11 kV in a particular spring, you can see that we have a rapidly increasing network peak demand in that early evening period. And as more and more customers have adopted solar PV, what we're seeing is that load in the middle of the day continues to be eroded, and can actually cause backflow into the network. In fact, in some of our localized areas of the network, we're seeing minimum demands that in magnitude can be equal to or greater than the peak demand that happens in the evening. And so we take a really keen interest in things that impact on electrification, on energy efficiency, or on demand flexibility, because they're all really important tools that we have as a network business to be able to address the problem that you can see on the screen now. So as the manager of the demand and energy management team, I run a series of demand flexibility programs. In a minute, I'll have a chat about the demand flexibility program for hot water. But that's one of many programs that we run, including our network connected battery program, our peak smart air conditioning program, and the programs we run to encourage the demand flexibility of electric vehicle charging. And all of those programs have been underpinned by cost-reflective network tariffs and have the impact or goal of moving load outside of the peak demand period and moving that load into the middle of the day minimum demand period. But on to hot water, because that's what we're all here to talk about today. The distribution network businesses in Queensland have had a very long history of operating hot water demand flexibility programs. These programs started back in the 1970s using our audio frequency load control technology, which is a signal that gets sent down the power wire to a signal receiver that's sitting just behind the meter. And it has the ability to turn off resistive storage hot water units. And in response for customers participating in those programs, they have been exposed to cheaper electricity rates. This program that we've operated originated to create an overnight baseload for our coal-fired generators to be able to continue to operate in the overnight period. But as Southeast Queensland continued to experience population growth, we started to see a lot of infill happen, and we also started to see an increasing adoption of air conditioning, which slowly started to increase our evening peak demand period. And so the program evolved into a peak lopping program. There's been yet another evolution of that program as we've seen more and more solar PV impact on the network. And predominantly in Queensland today, we use that demand flexibility capability to ensure that as much hot water as possible is heating in the middle of the day to soak up the excess solar PV generation. We've got just under 1 million customers who participate in that program, and it gives us 0.5 gigawatt of demand flexibility with a very, very high social license. That's really important for us because that program represents somewhere between 15 and 25% of our residential customer energy consumption. And with those resistive storage hot water units having an average instantaneous demand of 3.6 kilowatts, it's a substantial amount of load, and it's been operating as a pseudo battery that most customers have behind the meter. So that's where we've started, and heat pumps are here now. We do have a small number of heat pumps on the program. Should say we operate this program in a way that is beneficial, not just for the distribution network business, it's also really beneficial for the wholesale market and for customers as well. On the picture on the left, you can see the average spot price. And the period that is shaded in red is the period that we're moving load outside of. So we're turning load off during periods that typically have quite a high average spot price. And we're moving that load predominantly into that green shaded period that predominantly has a low or even negative average spot price. So that program has an implicit benefit for the wholesale market and the retailers. On the right-hand side, you can see what this looks like for the distribution network business demand. And again, in that red period, we're moving load outside of that red period, which is the network peak demand, and predominantly moving it into the green period, which is where we start to see localised network assets have minimum demand challenges. So one of the benefits of hot water demand flexibility programs is that it benefits the retailer or the wholesale market, it benefits the network, and it benefits the customer. So there's a bit of a win-win-win there. I'm cautious that solar soaking is an absolutely fantastic thing, and we encourage solar soaking, and we love to see energy efficient appliances operating when the sun is shining. And 360 days of the year, this is a fantastic outcome for network businesses and for the market and for customers. I do know that there's 3 or 4 days of the year where we have abnormal peak demands hit the network when we have a cloudy day, and that demand flexibility is really important there so that we can ensure that load is not appearing and adding onto that network peak. And so that means that the type of demand flexibility we have is relevant. And as a network business, we're not seeking to have demand flexibility every single day, but just in those days that really matter. So a key point here is that making loads flexible at the point of electrification is going to enable customers to maximise the value of their investment and their upgrade in a heat pump. But here we are, we're talking about heat pumps, and heat pumps are different to resistive storage hot water units. And so we need to take a fresh look at what does demand flexibility look like in that new environment. We're aware that heat pumps are more energy efficient than their resistive storage counterparts, and so less energy is going to be required to heat the same amount of water. And we are in support of that electrification and that energy efficiency, but we're conscious of the impact that that will have on network minimum demand. We're thankful and recognise that heat pumps place less instantaneous demand on the distribution network, which can really lower the risk of heat pumps contributing in isolation to network peak demand, and also aware that heat pumps require a longer period of uninterrupted supply compared to a resistive storage hot water unit. And so that needs to be taken into account in the way that demand flexibility is operated as well. That said, the accumulated impact of millions of customers with heat pumps is still going to cause impacts on the distribution network business if it's not appropriately managed with demand flexibility. And so again, I'll just reiterate the key point from a distribution network perspective and from the perspective of enabling customers to absolutely maximise the value of their investment in a heat pump. We need to ensure that they are flex enabled at the point of purchase and installation, so that that customer can present their load to the network and to the market in a way that helps them save money. And Rachel, I might pass back on to you now.
Thank you so much for that, Candice. Our next presentation also focuses a bit on heat pump hot water, but don't worry, we'll branch out in presentation 3. But for now, I'd like to welcome David Roche, Research Director, Strategic Energy Collaborations at the Institute for Sustainable Futures, University of Technology, Sydney. David, if you would like to take it away.
Thanks, Rachel. Let me just get my screen sharing up. I take it you can see that okay? Yeah, welcome everyone. So I'm going to be talking about heat pumps and building on what Candice was just talking about, also talking a little bit about resistive hot water systems, and particularly on 2 research projects that we've been involved with. The first one being this one published in 2023, which was commissioned by ARENA, where we looked at domestic hot water and flexibility. As you can access the report using that QR code if you like. Just a couple of key takeaways from this work. So we did some modelling on different scenarios for electrifying the fleet of hot water systems across Australia. We have quite a high proportion of gas systems. And so we modelled 4 different scenarios, a kind of business as usual, as well as various levels of decarbonisation of the domestic hot water system. And we found some quite stark numbers. So in terms of the amount of flexible demand capacity that we could add to the system, it works out about 24 gigawatts by 2040. We could lower costs for customers by between $4.7 and $6.7 billion in total. So that works out at around about $660 to $960 per household. And on top of that, we also reduce emissions by 3 to 5 times compared to baseline. And the reason that we're reducing emissions so much is that if we look at emissions from the electricity system, they're rapidly reducing as we decarbonise electricity production. So this shows emissions intensity for the grids of New South Wales and Victoria. And already looking at some more recent analysis that we did, we find that both resistive systems and of course heat pumps are less carbon intensive than gas appliances going forward, even for the most emissions intensive state, which is Victoria, and certainly for other states, they're less emissions intensive technologies already. So at the core of the exercise was this central question, which I think Candice alluded to as well, which is really about the sort of efficiency of heat pumps on one side of the ledger versus the less efficient but more flexible technology, which is the old style resistive hot water systems. And one of the key takeaways from our work is that it's not one or the other. I think we need a combination of both in terms of the way we roll out demand flexibility across the system. And it really depends on situations such as, for example, does the customer have rooftop solar? Is there suitable outdoor space for a heat pump? So we can have this kind of decision tree approach to deciding what is the best option in terms of the technology that we put in, but also what is the best option in terms of the way we enable the flexibility of that technology. So moving on to our more recent research, this has been a project funded by Race for 2030, where we're looking at a heat pump pilot as a big part of it. And a big part of this is developing some guidelines to assist community housing providers. So there's a market scan in here where we looked at all the different heat pump products that are available across Australia and looked at their specifications. We've done some detailed comparative analysis and developed some decision-making tools. And we also have data that we're collecting on heat pump operation, which we're providing to the two networks involved in this project, which is Ausgrid and Essential Energy. The design guidelines are essentially an easy to follow guide for community housing providers. There's an emphasis in there on electric technologies, especially heat pumps. It's not released yet, but it's coming pretty soon. And in terms of the topics covered, it looks at the product specifications. So things like, what material is the tank made from? What's the temperature range? Does it make any noise? Those sorts of things. Application. So for example, what sort of home? What's the layout of the home? What's your location, climate zone? Do you have solar? Those sorts of questions. Costs. So there's quite a bit of techno-economic analysis looking at both capital, operating and maintenance costs. And then other key indicators, things like greenhouse gas emissions. And all these things kind of interact in different ways. So this is kind of a mud map, I guess, of the guidelines in terms of the different sections and how you might sort of cross-reference from one to the other. The pilot itself, we've got 172, I think, homes in the pilot, but only 59 of those we've fitted with these watches devices that enable us to monitor energy usage in detail, but also to control the systems. And so that's been quite useful for generating quite good quality data. So for example, here's something we looked at, which was the variance in the amount of time that's taken for the systems to operate. And so we found quite a lot of variance, meaning that, for example, controlled load 1, as Candice alluded to, is generally not acceptable for heat pumps. We are recommending, if they're going to be on controlled load, that they be put on controlled load 2 rather than controlled load 1, just because the amount of time required for them to operate is higher than it is for resistive systems. Energy savings we also looked at. So here's an example of 4 homes where they went from a resistive system to a heat pump, and not surprisingly, they saved quite a bit of energy, and the order of 74 to 83% over this period that we looked at, comparing one winter to the next. And that translates into estimated bill savings of between $11 and $56 per month for that period that we looked at. In terms of greenhouse gas emission savings, we also see quite substantial reductions. Again, this is using the data that we collected from the watches plus the bill data and estimating emissions from the 2 different technologies. So for this one winter period, we're seeing emission savings of between 62 and 72%, even taking into account the sort of varying emissions intensity of the grid from time of day. And in the pilot, we also had a small number of systems that were electrified, so going from gas to electric. So this is an example of a 2-story unit complex that had some aged centralized gas systems. And we estimated the efficiency of those gas systems at around about 26%, so pretty old, pretty inefficient. And they were replaced with some nice new heat pumps at over 300% efficiency. And so we, again, unsurprisingly, but it's quite a stark kind of drop in the energy consumption for each of those units, just in terms of their hot water usage. And again, that translates into quite substantial bill savings for customers. So in this case, between about $700 for one customer, over $600 for the other, and greenhouse gas emission savings of 480 to 324 kilograms per annum. Now, as we've been talking a little bit about controlled load, as Candice was introducing, so we've also been looking at this in the pilot as well. And so we did a controlled load intervention, or two of them, in fact. So we looked at controlled load 1 and controlled load 2, and we had to be quite selective in terms of the units that we put into them because we didn't want people to run out of hot water. And so the difference between controlled load 1 and controlled load 2 is that controlled load 2 has 2 periods of operation instead of 1. So both during the daytime and also in the evening, but both of them avoiding both the morning and evening peaks. And so as a baseline, we looked at uncontrolled operation across the cohort, and we saw that there was a peak pretty much in the evening when you don't want the peak to happen. And then we put things onto controlled load 1. Again, unsurprisingly, perhaps they operate during that window that we've set for them, which is that they all sort of switch on around 8 or 9 o'clock in the morning and then operate through to 4 o'clock. And we didn't see too many problems with people running out of hot water. For controlled load 2, we had a similar intervention with the 2 periods. And again, we're seeing that the units operate during those periods. Interestingly, the evening peak seems to be a bit higher than the midday peak. And again, we sort of didn't see any problems with people running out of hot water. But there's a little bit of variation across the cohort. So this just gives you a bit of a flavour of the different types of profiles that we saw for each individual unit. So talking a little bit more about control and the different ways we can control hot water systems, it's clear that the benefits of controlling hot water systems accrue to the different stakeholders in different ways. So the benefits for a resident are largely in terms of things like bill savings, and the bill savings depends on if they have solar, they need to sort of fit their hot water system under their solar curve. If they have a time of use tariff, they can save money that way. The housing providers, in this case, they want things that are not too complicated and don't require them to go out and have to service units or increase their risks in any way. Whereas the networks are going to be benefiting from the controllability of units. And so the different types of control strategy give different benefits to those different stakeholders. And so we kind of map those out in this case to look at, well, which of those control strategies actually gives the kind of best option. Things like smart timers, generally a pretty good option, but not something that's widely available in the market. Inverter signals also score quite highly. But things like timers and so on, not always the best option for either networks or for customers. And so this is, getting back to this sort of decision tree idea, we've kind of used that framework to map out the different decision points for a community housing provider in terms of how they would perhaps enable control of hot water systems. And so we start with, does the tenant have solar? Yes, no. If they do have solar, is there a control method that can be implemented that benefits the tenant without unnecessarily increasing risks? So yes, no. And so we go down this tree and we end up with sort of different outcomes depending on the exact scenario. And there's quite a few variables in there, so solar being one of the key ones, but also things like, is the unit, the controlled load, the heat pump unit, is it compatible with controlled load, for example? So we've seen in our market scan that not all systems are fully controlled load compatible. And finally, we did some financial analysis to look at the different operating costs, but also the different lifetime costs of different options. And so this just gives you a sense of the different tariffs that are available. So on the left, we have sort of flat tariffs where the blue circle is just a constant 30 cents a kilowatt hour during the day. The red circle is the feed-in tariff for solar. So if you're operating off solar, you get essentially a much lower opportunity cost for operating your system off your own solar rather than using power from the grid. And then also we looked at time of use tariffs, which is what's represented on the right. And so in terms of operating costs, we saw that the electric systems varied quite a bit. The gas systems were amongst the most expensive. But the electric systems really depends on whether you're using solar or not. So if you have access to solar, you can get very cheap operating costs. Whereas if you don't have access to solar, electric resistance systems can be among the most expensive systems to operate. And in terms of the lifetime cost, that translates into, again, electric resistance systems can be either the cheapest or the most expensive system, depending on whether you have access to cheap solar or not. And gas among the more expensive systems. So we think there is a role for heat pumps, and they're certainly one of the cheapest systems to operate, but in terms of lifetime cost, they're more expensive in terms of capital. So we think we need a bit of a mix of both. And finally, just in terms of greenhouse gas emissions, again, we find the electric systems are among the lowest in terms of emissions, gas systems much higher. So I'll leave it there and I'll hand back to Rachel. Thanks.
Fantastic. Thanks for that, David. I'd now like to welcome Lou A, Professor in the Department of Infrastructure Engineering at the University of Melbourne.
Thank you. Are you able to see my screen?
Yes.
Yep. And this is the report that we have written. This is a part of Annex 88. So in my presentation, I would like to tell you a little bit about Annex 88 and what we have done and the project duration. We started in the 1922, and then some of those we can't meet face to face. So we did it during COVID through, web, what we call Zoom and other things. So we have output out of that one. And first thing is acknowledgement. We already acknowledged to the country. So first, I would like to acknowledge our authors, reviewer, and editor of the State of the Art report. These slides will be available. If you go back, this is a link there that you can see. And if you click it there, you will get that link. This PowerPoint PDF will be available. And another one is Stanford. Allow me to participate as a country representative, and Ned and Rachel for helping me with this. So Annex 88, if you go to that our website, you will see our operating agent from Japan, and this is ongoing at this moment. We will finish 2027, end of June. So what are the issues we are going to look at? We are looking at right now is that if you look back the tested performance that we tested in the lab and then real world performance, they don't match. And lack of standardized load-based testing. So we don't have that load-based testing standardized, and we don't have insufficient fee monitoring data. And some of them are dispersed, some of them are available. However, if you are going to do artificial intelligence or extracting the data out of that, that's not enough. Especially Annex 88, looking at the interaction between heat pump and building, how do they perform in building? So we intentionally leave out hot water, and we look at building cooling and heating. That's mainly Annex 88 look at. Yeah, we have another IEA Annex looking at the hot water issue and heat pump hot water. Those are the things. So that's why we leave out, hot water system in here. And another one is a inefficiency. We found that some of those are from improper sizing and installation. So we look at 4 areas: testing methods, fee monitoring methods, and then how do we calculate the performance while we are applying in building, and how do we design our system. So these are the objectives that we aiming for out of this what we call annex. And participating country, and at this moment US is thinking about participating, but we haven't got official participation yet. And one person from US contributed in writing this report. This report is freely available, 182 pages there. So this is a sort of extract from there. First thing is a lab test on the left-hand side, and the right-hand side is a load-based test. What is the difference? The important things in there is a fixed compressor speed that we do normally test it in the lab for rating our system, and if you are a manufacturer, and we require to do that one. Okay, so on the horizontal axis you will notice the time, and this is a sort of steady state test. And on the right hand side, if you look at the test, it's about 7 hours. So this is, as you can see, this is unsteady and real life operation simulated in the what we call test in the lab. Okay, important one, and I would like to show you, is a COP difference. It's very simple in here. If you do steady state test in a certain fixed condition, your coefficient of performance or energy efficiency or whatever we say is about 7. So if you are going for dynamic tests or the real life test or simulated real life test, you will find that about 5.5 COP. So, and this is misleading for when you are applying this. We might be expecting, rated is 7, COP, and in reality, we are having that. The reason is that the lab testing is different in real life. And this right-hand side figure, it's an emulator. We do it in the test. This can be repeatable, and we can do the test. And what we found is that this is very much closer to the real-life operation, sort of. And this is a finding from that 2 document there, and the PowerPoint is available. If you go to the link, you will see that full presentation we have presented in last year. And the second one is a field, what we call test COP, and the rated COP. On your horizontal axis on this graph, you will see the partial load ratio. Partial load ratio means the capacity of the heat pump, maximum capacity of the heat pump, and how we running. Heat pump doesn't run full load all the time, so there you can see partial load, and these are the test measure field test data, actual measure data, and you will see the outdoor temperature range 0, -3, 6, 0, 3, 6, 9, and 12. You can see those symbols there. And you can see the 2 important ones there. It's a test according to the Japanese standard for this circular one, and the middle capacity test, and then rated capacity according to that, and the full load capacity is in the catalog value. You can see that. And in reality operation, you can see the left-hand side, you have a lot of dots, and heat pump is operating in partial load ratio. So if you got a partial load ratio very low, your COP will be low, as you can see. So important point I want to make in here is that field test is the one tell us the performance that we are going to get when we apply in the building. And these are some findings from calculation methods, and Lawrence presented in December. And his finding is a different country have different dominant need. For example, in European country, they will need heating. For example, in Australia, we may need, some of the area, they may need only cooling. Some of the area will need heating for the building. So they also have a different types of system, and water-based or air-based. Some of those provide hot air or chill air, or in Europe, you will see that chill water supply or hot water supply. Heat pump can do all sorts of things in there. And when we look at the calculation method, we found that a lot of different types of heat pump there, and the heat source, where the heat you get from, and where the heat transfer to. You transfer it to your room or you transfer it to your hot water, and how do we control that? And what are the other things combined together with the heat pump? Heat pump is using for drying or other things. However, we are looking at in here design methods applicable for the buildings. So many types, so we don't have clear product data. And international wide, if you are going to import something from somewhere, some other country, you got to meet the standard requirement, and you got to declare these are the star rating or performance required. And it's harder to what we call export and import doing thing. They got to do it again. So what we also find is that none of them are completely or fully reliable, and they are very disparate. Okay? And data needed depends on the method that we use. And that's why we need to have an expert from heat pump and expert on energy performance. So they need to work closely together. Yet some of you may be, both expert in those areas. That's all good. You will understand the problem there. Okay. And we need to find a balance between the effort required, how do we test those? And then we got to find that, what sort of accurate prediction that you need. So we got to do that. Calculation methods need to be balanced in between these two. And this is an existing guideline or the standard that we have reviewed. And I was in charge of reviewing that. And then we have a team of researchers reviewing those. And they have contributed in that report in chapter 4. And I'm not going to go into detail for individual, what we call standard, what they do. An important one in here is what we are going to do in the future. And we are develop sizing procedure for heat pump that may be applicable, universally applicable, hopefully. And we are aiming very ambitiously. And then that's end of 1927, sorry, end of June 1927 that we are expected to deliver. Okay. And how do we avoid the low partial load condition to improve the efficiency? So this thing also, it's an important aspect. And how do we incorporate in the control system? These are the issue there. And another one is a quantitative information for different, specification and product selection. How do we select those and how do we use it in energy calculation methods? These are the ones that we are aiming for. It's a future work in part D. That's one design guideline parts. And these are the take-home messages and mainly intended for industry and the policymaker. And system design and installation, as you already know, proper sizing, optimized control, and correct installation, these are important. And the testing methods, and these are also what we call, they need to reflect the real world operation condition. And we test it for steady state, and then in reality, we use it for dynamic, in real life situation. So how we are going to estimate how they are going to really consume energy. And another one is performance data. If you are going to do anything, data is a very important one. So you need to know that data, and we need to have that various applicability around the world, and then so that we can identify inefficiency, why they are not performing as they expected. And another one is the energy calculation methods and standardized accurate model. We are trying to develop that one, part of NX 88, and we will see whether we are successful or not end of what we call project period. And we are trying to develop design guideline. It should be clear and the practical guideline, and it will tell us how to size, system configuration and control strategy, and which you can enhance the efficiency and reliability. And another one is that policy and regulation are important, and industry should collaborate with policymaker to be aligned with the standard, certification scheme and regulation with real world performance data. And what we want is a heat pump technology. This is well developed. However, if you use it in real life, we got to make sure that they really save energy and they really solve our problem. And the last one is a bit of selfish for us, and R&D and trainings are very important. And I would like to say, give us money to do research. Many thanks. And that's my contact email address, and feel free to send me email.
Thanks very much, Lou. And what a great spot to leave us on. Give me more money. I'd invite the other speakers to pop your cameras back on now, because we are up to the Q&A portion. A reminder to use the Q&A function if you have a question, and jump in and have a look at the questions and pop an upvote on anything you'd really like to see us address, because we're using that to triage the questions. So with that, there are two questions that have a number of upvotes that are quite connected. So an anonymous attendee asked about installation considerations and whether or not heat pumps can be installed in enclosed plant rooms. And Alan Peers also asked about whether or not there's been work done that anyone knows about regarding heat pump hot water systems indoors. So regions that need home and space cooling, apartment dwellers, things of that nature. So connected, the indoor use of heat pump systems, particularly hot water. Does anyone have any views on those?
Yeah, it's not something that we've done a lot of work on, or that has come up a lot in the Australian context. But certainly in overseas markets, there are, recommendations to put heat pumps in basements, in, garages, sort of big airy spaces. But in terms of actually putting them inside, the home where people are living, I know that happens. I think in Japan that happens quite a bit. But yeah, I haven't seen many examples of that in Australia.
Fantastic. Does anyone else have any thoughts, or really we just don't have many examples here? Lou, you got your hand up.
To be able to add what we call David answer, Ellen, you asked the right question or difficult question. In terms of theory, heat pump can operate both heating and cooling, right? If it is an enclosed space, you got to make sure that depends on where you reject your heat or where you get your heat from. So somewhere it need to be connected with the environment. So you need to think about rejecting heat or the extracting heat from the ambient. It could be you pipe it through to the system, or we got to do something. That's my simple answer, Ellen. Maybe Ellen yourself may have practical experience than me.
Thanks for that. We might move on to the next most popular question with a whopping 5 upvotes. Are electric heat pumps more efficient than gas systems in terms of emissions because of the decarbonisation of the grid, or are they actually more efficient when compared on a one by one energy metric? So are they really more efficient, or is it all about the grid?
They're certainly more efficient. Yeah, much more efficient than gas in terms of the emissions. So the emissions intensity of gas versus resistive systems. If you're looking at the grid of 10 years ago, you would say that the gas is less greenhouse gas intensive. But certainly, if you're comparing it to heat pumps, using about a third or a quarter of the energy, even of the grid of 10 years ago, the heat pumps are much less greenhouse intensive. And as we decarbonise the grid, that becomes obviously more so.
Would anyone else like to add to that, or? No, you answered it perfectly.
I would add, if you have a very bad heat pump, you could have a bad heat pump with a very low COP. They may generate more greenhouse gas emission. Some of those, some people might claim heat pump COP 7, or in reality, they may be 3, less than 3. If it is less than 3, they will not perform as you mentioned. Yeah, generally it's fine, but we need to look at specific, detail. If you want to generalization, that's good. But in reality, we could find, that's my academic questions. Sorry, David.
Yep. Actually, there's another point there in terms of emissions that we didn't touch on. It was buried in one of my slides about the emissions from the refrigerants used in heat pumps. So there's been a move away from high greenhouse warming potential refrigerants towards lower greenhouse warming potential refrigerants, which is a good move. But yeah, if you do calculations, and you're using a heat pump with a very high refrigerant, high potential refrigerant, then you could, in theory, sort of offset some of the gains you're making, or quite a lot of the gains that you're making from switching to a heat pump. So, but yeah, glad to see that we're moving in the direction of having much lower emissions refrigerants.
Fantastic, thank you. So we have a question that has come in. Sorry, my screen has decided to readjust mid-sentence, which is always very helpful. We do have a question around, do we understand what the real life parameters are which cause the difference to lab test, and can they be reproduced in a lab? Always topical, this one. Does anyone have any thoughts?
Well, real life, and we tested in the lab to make sure that it's repeatable. Real life, we may not be able to repeat, very hard to repeat real life. And if you look at heat pump performance, depends on let's say if it is for heating, it depends on where we get the heat source from. It could be ambient air, or it could be you are getting the heat from the ground, okay, ground temperature. And another thing is ambient air got a temperature variation, and ambient air got the relative humidity variation there. And the compressor, if you have the compressor, if you could control the compressor, or it depends on a lot of variables, it can happen. In reality, heat pump performance mainly depends on two things, okay? Your equipment, like your compressor, and plus your heat exchanger, like condenser or the evaporator, or the temperature between your condensing temperature and the evaporating temperature. And they all affect a lot of things in there. And especially if it is a building, load. Depends on how you use the load. Load could be sensible load, like the temperature heated up from the equipment. And that could be also from latent load, like the moisture, generating from, you have that, kettle or cooking or whatever, those sort of heat load or the cooling load, whatever inside, they will also affect all sorts of things, And as you know, the load and the occupant ourselves, for example, we generate what we call, for example, for cooling, we generate our overcell heat. At the same time, we generate sweat and we breathe out, fully what we call moist air out of our breath and those sort of things, they all happening. So it's a very dynamic. So to be able to repeat that, a lot of variables involved. Yeah.
Do we have any further thoughts on that one? No. So noting that there's been a number of questions aimed at Lou and David, I wanted to pass on a few, or one that's come through to Candice. So there were a few questions around the cost benefits and how they're passed on to consumers, which you might have some insights on. David may also have some insights based on your research, but there was definitely a few questions with that theme around, well, what are the cost savings and how are they passed on to consumers? So it'd be great if you could give us some insights.
Yeah, absolutely. So the primary way that distribution network businesses pass on their portion of the benefit to the consumer is through the distribution network tariff. And thankfully, that benefit then flows through to the resident who's paying for the electricity bill. So provided that the tenant is paying the electricity bill, they should get that benefit. One of the challenges of that mechanism of passing through the benefit is that retailers aren't obliged to pass that benefit on. And so there are some differences in how different retailers will pass through that benefit. And they may indeed choose to bundle that benefit into a broader package that may become less visible. But that's how we typically do it. It's not really through incentives. It is through the distribution network tariff that consumers will receive that benefit.
Thank you. David, were there any observations in your research?
Look, it's really, I mean, Candice has sort of summed it up. It's really about tariffs, but also just the, sort of the direction of gas tariffs in Australia is certainly not going down, and people can self-consume with solar. So there's a lot of ways to operate electric technologies very cheaply, which isn't available for people if they have gas. So in terms of electrifying, that's where most of the benefit is coming from.
Fantastic, thank you. We had a question that's got a couple of upvotes from an anonymous attendee, just wondering about how feasible it is to use heat pumps in settings like sports centres where there's, really quite extreme peak demand after games when everybody's jumping in the shower. Is that sort of practical, or is this maybe not the best application of these?
I'll jump in there. It's going to be a better application than resistive storage. Hot water definitely would be, because that would place even more sort of volatile peak demand on the network. So encourage that. But I think one of the comments there has been to investigate the use of a commercially sized heat pump as opposed to multiple individual ones. Something to consider there.
Absolutely. Thank you. So we do have a question here, which I'll just read out from another anonymous attendee who is asking, does sizing procedure of heat pumps consider degasification or like for like, bracket, heating capacity, fuel switching and associated emissions? I'm not
Well,
sure. Yeah.
it would depend on what we are aiming for. If this the aim of this, reducing the greenhouse gas emission, yes, that we should be looking at. We have that discussion long way back. And should we be focusing on that, or should we make sure that it works and it performs? And performance, which is the important performance, or greenhouse gas emission per kilowatt hour of heat provided, or greenhouse gas emission per kilowatt hour of cooling, or what is the objective function? So we got we don't have a fully agreed, and also it depends on the focus, what you want out of that. You want to maximize your money saving, or you want to maximize whatever you want to do. And the design method should be able to tell if you are doing this design, you will get the best performance. However, that may not be the best for your financial things. So, well, at the end, money is not that important. Important for us. However, yeah, we got to think about bigger picture, I think. Yeah.
Thank you. So there's a question here regarding temperatures. So is it true that a heat pump works harder, needs more energy to run if there's a higher or a lower temperature outside? I'm sure you all are in a position to provide an answer, so feel free to jump in.
Yes. Very simple answer.
TLDR. Yes. That is true. So does anyone have any thoughts about climate zones or anything to add, or are we happy with yes?
Important one is you need to think about where your compressor or the equipment works, where you are getting the heat from in terms of heating application, where you reject the heat. The temperature between these two, if they become closer, compressor need to work lower. So your efficiency, energy requirement will be less. However, if you change that difference between where you get the energy from and where you are providing, for example, hot water, and if the ambient, you are getting it, if the ambient temperature is hot, your compressor doesn't need to work very hard so that your efficiency will be better. So the difference between condensing and evaporating, or difference between heat source and heat sink, depending on your application. That's a bit of technical. Yeah.
And Rachel, you sort of mentioned this, but certainly in tropical Queensland, where you've got very high temperatures, then I do think that there is a climate zone sort of consideration to be made in terms of what the right mix is. And David spoke earlier about the fact that we do need a combination of technologies, and there's not really going to be a one size fits all, but it is certainly a consideration for some of those higher temperature tropical areas like Queensland.
Fantastic. Thank you for that. So we've had a couple of questions sort of hovering around commercial buildings and apartment buildings. I'll read you one from Chris, which is there a heat pump solution for apartment buildings where each apartment has, individual, for example, instant gas, given that retrofitting a centralized hot water system is likely to be an option in this case? So does anyone have any thoughts? Or just on the apartment commercial space and the use of heat pumps in that area would be great if you've got any comments on that.
Yeah, I might jump in because we have been doing quite a bit of research in this space, looking at apartment retrofits, not just for hot water, but for other technologies. And it's certainly it's a gap in the market, and we identified that in our market scan. So we think there is a need for smaller size tanks, heat pump units that are suitable for apartments, perhaps suitable for being wall mounted. So we've actually just recently heard from one of the manufacturers that there's a product that's available in Japan that they're looking to maybe import into Australia. So we've been talking to a few manufacturers about maybe piloting some technologies in that space.
Fabulous. Thank you for that. We've had a question come through for Candice asking what you would see as the ideal outcome for heat pump management, so IoT control HEMS, whilst the benefit of networks, operational cost to end consumer, making sure the customers still delivered comfort, whether that be hot water or something else, when they need it.
Yeah, my preference is always going to be that the tenant has the ultimate ability to control the load and therefore the impact on themselves. So anything that gives them the ability to shift their load into periods of the day, maybe using an inbuilt timer, would be fantastic. It is somewhat expensive to set up the control systems, and so if we had that capability inbuilt, I guess that would be our preference. If there's not a peak demand problem to solve, we then don't need to go and set up systems to control it. Sometimes that isn't possible, and so my next best preference would really be that there's a consolidated whole of site approach to managing consumers' load that might vary in accordance with a dynamic operating envelope. And so things like HEMS can be quite powerful there, although the technology at the moment is quite expensive for consumers to adopt.
Thank you very much for that. I note that we've only got a couple of questions left, one of which David looks to be typing an answer to. So in the interest of finishing on time, I think we will leave it there. But I'd really like to thank our speakers for coming along today and taking part in this webinar. Thank you to everybody who logged on. As Nat noted in the chat, we will circulate slides and other details discussed today to all of you after the fact. So you'll have the opportunity to review that, and you're also welcome to reach out to the EEC if you have any other questions from today. But otherwise, I think we will finish a whopping 2 minutes early. Thank you all very much.
Sorry to interrupt. This is
Sure.
message for Ellen Pace. Ellen, your question has been answered personally through Q&A. Before we close this, you should get that answer, Ellen.
Okay, no worries.
Sorry.
Yes, no problem at all. And I can see David's still typing, so I'll leave it open. But I would like to invite everybody to log off, and we'll conclude the webinar here.
Thank you, Rachel.
Thank you.
Thanks, everyone.